This is today, yes. Oh, I think that is today, yeah. Well, actually, this is Thursday. All right, guys, so we're looking at writing equations of linear functions. A linear function is just we're going to define function in a minute here, but it's a relationship between you. It's like you give me an x value, you put it into the function, out comes a y value, and if you graph a series of those, you get a bunch of dots that are in a line. So we're going to be studying linear functions, writing equations for lines, etc. So a few definitions here. First two are the dependent variable and the independent variable. The dependent variable changes in response to another variable. It's known as the output. In Algebra 1, we often use x and y, and this would be the y. The independent variable doesn't change or depend on another variable. It's the input. In Algebra 1, oftentimes that's the x. Okay, but understand that those variables could change. So you could use t and s, or t and v, or something like that. A function. From this point forward, we're going to be studying functions in mathematics, a bunch of different functions, primarily in Algebra 1 and Algebra 2. But a function is a relationship that pairs each input value with exactly one output value. And in the first semester of Algebra 1, which is where we're at here, we focus on what are called linear functions. Next semester we focus on quadratic functions. But linear functions are of degree 1, we say. They are of degree 1. That means the power on x, or the power on the independent variable, is 1. So a linear function is a function whose graph is a line, but not a vertical line. So you may have seen these before. These are little function machines. We have an input, an x, put it into the function machine, and we get an f of x or a y. So this is called f of x. F of x is how we say that. And it's the function evaluated at x. So we'll start seeing a little bit of function notation, which is probably new. So here's a function. We have f of x equals 3x plus 1. So here's what it looks like. We tell the function to plug in 3 by putting the 3 in parentheses next to the f. So f of 3 is how we say this. F of 3 is equal to 3 times 3 plus 1, or 10. So f of 3 is equal to 10. The input is the 3, the output is the 10. The independent variable is the 3, the dependent variable is the 10. So that is a linear function. Next semester we'll be studying what are called quadratic functions. So if we take -2 and we plug it into the g of x function, it's g of -2 equals -2 squared. Remember, -2 squared means -2 times -2 should be a positive 4. So you could, there are lots of different functions we study. These are the primary two we study, types that we study in Algebra 1. As you move into Algebra 2, you end up studying many others: absolute value functions, square root functions, rational functions. we'll look a little bit at those in Algebra 1, but not much. So those are functions. All right, representing a geometric relationship here, we're going to combine a little bit of geometry, the idea of perimeter, with a linear function. See, perimeter is one-dimensional, right? Perimeter is just length. So it makes sense to connect perimeter with a linear function, whereas area is two-dimensional, right? So there's the mathematical model for area would be a quadratic function, or something with an x squared in it. And then volume is three-dimensional, so you would have what's called a cubic function to model that, x cubed. So we're going to focus on just perimeter here. Let's go ahead and fill out this chart. We're going to look at this if we have just one rectangle here. So say we have one rectangle. The question is, what's the perimeter if we have this one rectangle here? Well, we're going to plug in 1 right here because we have 2 widths of 1, and then we have 2 lengths of 6, which gives us a total perimeter of 2 plus 12, or 14. And an ordered pair of 1, 14. The ordered pair is what we'll graph. So if you look at this first picture, it's just saying with one rectangle we have a perimeter of 14. If you put a 6 here and a 1 here, you'll see that those add up to 14. What happens if we place 2 rectangles side by side? How does that change the perimeter? Well, now we have a 6 here, a 6 over here. So that hasn't changed. What has changed are the widths. The width is 2 by 2, and so we end up with 2 rectangles, gives us the equation 2 times, oh boy, 2 times 2, this was 2 times 1. 2 times 2 is 4, plus 12 is 16, so that gives us an ordered pair of 2, 16. So the perimeter is the y, and the number of rectangles involved in the shape is the x. The next one, I plug in 3 here. It's not cooperating. Give me a moment here to try to calibrate this thing again. Maybe. Oh, maybe not. All right, try it again here. So now we're plugging in 3. Okay, did not work. 3, 2 times 3 is 6. This is 2. This is 16. And this is now 18. So we have the ordered pair 3, 18. And then the next one is 20. Yeah, you can usually pick up on the pattern. So this is going to be 20. And the ordered pair is 420. So in words, what's happening? Each time I add a rectangle, what's happening to the perimeter? Yeah, by what? Each rectangle added increases perimeter by, and I'm going to write down in a different color here, by 2. I'm going to show you where that 2 comes into the equation for it. So if you think of perimeter as y and number of rectangles as x, we have y equals, we're going to take this number right here, this number 2, and that's going to become, number in front of the x. So you have 2x plus something here. So let's figure out what the number is. Well, it works like this. The 2 is what we call the rate of change of the perimeter. It's also known as the slope. Okay, if you've heard of that term before, we'll talk more about that later. But the 2, this difference as you go from one y value to the next, will always go here. So y equals 2x plus something. Now, if I plug in 1 here, 2 times 1 equals 2. What do I need to add to 2 to get up to my first y value of 14? 12. And so that is known as the y-intercept of the linear equation. So every one of the tables that you're dealing with in today's homework and classwork will be like this. They're all linear. So they'll go up by a constant rate. That constant rate is the number in front of x. And then they're either going to start at 1 or at 0, depending on the context of the problem, and so that'll change what your y-intercept is. But then you're going to be asked to plot these. I'd like you to plot these just as a discrete graph, meaning just separated out points, not connected. You'll notice that they are linear. So the first one is 1:14. Second one is 2:16. Third one is 3:18. Fourth one is 4:20. And so just leave it like that. Sorry, I'm doing the best I can with this thing being out of coverage. It's struggling here. Just keep getting that pop-up that my computer's running slow. It's true, it's having difficulties this morning. So you will look at the pattern in the table, write an equation, explain in words what's happening, and then plot the points. That's what you're going to be asked to do on each one of these. All right, one for you to try here. So this is with triangles. In the diagram, what is the relationship between the number of triangles and the perimeter of the figure they form? Represent the relationship in a table, words, and equation, and graph. So when you have one triangle, here's the setup here. Here's the setup. It's just like the last one. With one triangle, notice as we go from one triangle to 2, what's not changing is the number of 3's you see in each one. Do you see that along the side? So that's the fixed number. There's always 2 3's. But what is changing is the number of 4's you see here. So with one triangle, there's 1 4. With 2 triangles, there's 2 4's. With 3 triangles, there's 3 4's. With 4 triangles, there are 4 4's. So your table would look like this. With 2 triangles, you would have 2 4's, 1 4. Oh, goodness. With 3 triangles, 4 triangles. And so, if I can get this to work here, maybe, the fill-ins would look like that. So you have 4 plus 6 is 10, and then 8 plus 6 is 14, and then 18, and then 22. What do you notice this is going up by each time you add a new triangle? It goes up by 4, yeah. Each triangle added increases perimeter by 4. So we're going to take that 4 and translate it into an equation down here. So we've got y equals what times x? 4. Yeah, 4 times x plus something here. Let's see if we can figure out the something. Plug in 1 here. 4 times 1 is 4. What do I need to do to make the jump from 4 up to 10?
Plus 6.
Plus 6, yes. 6. You should probably double check, so 4 times 2 is 8. Add 6 more and you get to 14. Notice what are each of these numbers, the 2 times 3 down here, they all equal 2 times 3, 2 times 3, 2 times 3, that's the 6 that we use for the y-intercept. Now, not all your tables will be as detailed as this one. They're going to ask you, I'll show you in the classwork, but just to make an xy table, called a t-table. You've done those before. So you'll just have the x and the y, and you'll be looking for a pattern in the y's. Remember, the constant difference is the slope, and then you'll have to figure out the y-intercept by plugging in the first value. So if we graph these points, we'd have 110, 214, and then 318. We'll stop right there. I think your graph only goes up to 20, but with 3 points, you can see that it is a linear pattern. It's definitely making a line. You know, any 2 points you can draw a line through, but as soon as you hit that third point, then you've determined the line, right? So we've looked at it with rectangles, triangles. We're finding linear patterns here. All right, the other thing you'll be asked to do is, given a kind of real-life scenario, a table here, it says the table shows the relationship between the number of photos, x, you can take, and the amount of memory, y, in megabytes left on your camera. Is the relationship a linear function? Well, is it going up or down by a constant? It's going down. So in words, we would say each photo takes away, switch colors here, 3 megabytes, MBs. And so where does that 3 show up in my equation? What's the sign on the 3? It's got to be taking away, right? So it's negative 3 times x plus, okay, another phrase we use for a y-intercept is the starting point. Notice x starts at 0 this time and not 1. If I were to plug in 0 here, negative 3 times 0 would be 0. What do I need to add to 0 to get up to the starting y value, 512? So when you have a 0 up there, the y-intercept is staring you in the face right here, okay? When there is a 0 up here, this is what we call the y-intercept, or the starting point, if you will. It makes sense because if you're starting with a card or a little thumb drive with 512 megabytes on it, that's your starting point. That's it. That's where you start with 0 photos. That should be the memory you have. And then we can go ahead and graph these points. So 0, 5, 12. When you're doing this on your own, you have to draw these graphs. 1, 509. What you'll want to do probably is do like they do here. It starts at 500 and then go up, or just have the values on the y-axis. That makes sense for the problem. There really should be a little break in this. It should be showing that there's a break. We're just looking at this one little portion of the graph. 2, 506, 3, 503, and you can see that that is linear and it is decreasing. All right. So we got some problems like that on there where there's a table and you have to figure out the constant difference. They asked, is it linear? I answered, yes, it's linear to everyone. They're all linear. We're going to mix it up a little bit once we introduce you to some nonlinear types of functions. This one's also a linear function. So yes, it is a linear function. Do you see what its constant rate is? Yeah, so I don't know what the real life scenario is here, but it goes up by 2. So our equation would be y equals 2 x plus something. What's the something got to be for this guy? 8. Yeah. And then we graph it. So 0, 8. I mean, visually you can tell this is linear as soon as you get 3 points on the graph. 110, 212, and then 314. So it is linear. So we've described the relationship using words, an equation, and a graph. And if they ask you, yes, it is linear. Okay. So in terms of a summary, the summary. What kinds of things could we put in the summary, maybe? I want to say something about the dependent and independent variable, right? You guys all get this? In our purposes, most of the time, the independent variable, right? I want to make a note that, I mean, it's been x, it's dependent variable in our circumstances in terms of x and y is the y. That might be new. What does it mean to be a linear function? You might say something about a linear function. Dots in a line or something like that, but you should know what a linear function is. So nonlinear would mean not in a line. We're going to get to that later down the road here. There's I think just 8 problems to try on here. So if you could, they use n. Here, I'll let you get started on that, and then I'll